1, 2, 3, 1, 2, 3. Okay. Hello, my name is Mateusz Owczarek, and something's going on. Okay. My name is Mateusz Owczarek, and together with Miron, Ficak, together we'll be introducing you into the world of probabilistic data structures and Kafka Streams as well. Without further ado, let's move on to the agenda. Firstly, I will try to talk something about Kafka Streams, mostly about the features and general concepts behind it. Then Miron will talk about his experiences with probabilistic data structures. And finally, it's going to be a commercial time. We're going to introduce you into the code, actually real code, behind our library that we developed lately that tries to solve the problem of connecting probabilistic data structures with Kafka Streams topology builders. Okay, let's start with the beginning. What is Apache Kafka? So initially, it was conceived as a messaging queue. At its core, it's a performant distributed commit log, but the times where Apache Kafka was only a performant event bus are probably gone. Now, I find it as a distributed event streaming platform, and all of it is because a Kafka Streams library has been introduced. What is it? It's just a lightweight Java library that you can include in your project that's based on any JVM language. It can be Java, it can be Scala, that enables transforming the data from one topic to another, I mean Kafka topic. The key feature of Kafka Streams is that no separate cluster for computation is required. Comparing it to the Apache Spark or Apache Flink, where Kafka is just a message queue, just an event bus that provides the data to the computational cluster, Kafka Streams reuses the actual Kafka cluster to perform a computation in a streaming fashion. It is code-centered. It has a Scala API, actually, not only Java API, but also Scala. And all the buzzwords are included. So it's highly scalable, it's fault-tolerant. It comes with all of the Kafka goodies, right? It is scalable with the Kafka partitions. It includes Kafka security and exactly once semantics. It is both equally viable for small, medium, and large use cases, because where Kafka Streams really shines are small projects, probably like a small projects under the 200, 300 lines of code. But nevertheless, Kafka Streams scales amazingly with Kafka partition semantics, so that it can be really nicely used in production as well in medium and large use cases. It can be also easily deployed to the containers, VMs, or cloud if you want, just as well as you deploy your production application. How can we use Kafka Streams? Well, on its core, it transforms messages from one Kafka topic to another. So it can be really easily used to perform Kafka-based platform integrations. There are some cases, probably that you know, that someone can use Apache Spark to just enrich and transform the data from one topic to another. And to do it, it requires setting up additional computational cluster. With Kafka Streams, you can perform it only with Apache Kafka cluster, and it's extremely useful. What's more, it can nicely fit in stream fashion alerting services and near real-time business intelligence streaming pipelines. Actually, probably in somewhat about 2 hours, there will be a talk about it, how Kafka Streams can be used in such a case as a production-ready example. So I invite you all to attend it. So what are the key features? What can you use actually inside of what features can you use inside of the Kafka Streams? The first one would be aggregation, and all of the stateful operations that Kafka Streams provides. What aggregation does is actually transforming n messages into one message. So it compresses the data input to the output. Aggregation is key-based operation, so you need to group messages by some key, and it may be both windowed and non-windowed. What does it mean actually for aggregation to be windowed? Well, for the non-windowed aggregation, as you may expect, it's a never-ending aggregate. So once you aggregate some data by any key, the aggregate would be run forever, or actually until you probably stop using your application. But the problem is, how can you divide the aggregates in time, right? So the answer is windowing. Popular examples are tumbling window and hopping window, and those would be explained in the next slide. But the very nice feature is that in Kafka Streams you may use time windowing by only setting three settings, three keys. That's going to be window size, window interval, and grace period. And the last one is extremely useful when you're handling with late events, when the events are not arrived on time. So the first example is about a tumbling window. Here on the input you can see two types of records. One type is colored with the green, and the second is blue. So you can imagine that those are two types of keys of these messages, and those are grouped into two streams and divided into 5 minutes time windows. In this image you can see the time window duration is 5 minutes. The unit is not present here, but you can imagine there is an imaginary mean written here. And the window interval is actually equal to the window duration. So that type of window we can call a tumbling window. Another example is a hopping window, when the window interval is smaller than the window duration. Then, as you may expect, numerous windows are aggregating the data in the same time. So yeah, what other transformations you can use with Kafka Streams? As I stood before, there are stateful operations like aggregate, and this is the most generic one. If you just want to transform, let's say, many messages into one message of the same type, you may use reduce, or if you want actually just to count the messages, you may use the count operation. There are join operations as well as aggregates. Those are windowed and non-windowed, and as well there are stateless operators like filter map, flat map. You can see those. So how to perform a streaming topology with Kafka Streams? This is pretty easy. What you need to do is to provide a stream builder instance and a properties instance. Those would not be described in this slide because, hey, I wanted to show you just the key features, right? The key code. So the properties that is shown right here, that variable contains information about the Kafka brokers, the host port of the brokers, and the partitions, and so on. And the builder you actually create just here. What you see here is that we accept messages of the key string, of the type of the key string, and the value is some kind of input event. The example here shows the unique word count problem, and this is a very naive approach to do it. I won't actually waste the time to describe all of it. I will include those slides probably somewhere later so that you can see about how easy it is to perform this. But nevertheless, this example, this solution is not performant. A unique word count problem can be solved for the big data in many other ways, and those solutions will be described on the next slides by Miron.
Yeah. So why do we need those probabilistic data structures? Before I start, a little disclaimer. I'm going to talk about distributed systems performance, which I estimated using my personal computer, so the exact values may differ noticeably from my results. Nevertheless, they are still interesting. So imagine we have a such case. We have organizations and visits of users in these organizations. Here are some numbers about the data set. 1,000 of organizations, 10 million of visit events per hour, 10 years of such history, and 1 billion of distinct users in total. Organizations are hierarchical, and hierarchy forms a tree. That means that, for example, if some users visit shop A, he also visits New York and USA and a huge company to which this whole tree belongs. And that also means that there will be a lot of organization with huge number of distinct users in total. So now some information about volume of the data. Visit events are in form user ID, organization ID, and timestamp. We have 860 billions of events in total, which sum up to 90 petabytes of raw events in total. And we want to solve such a problem. Answer how many distinct users was in some time range in few organizations. And when time range is subset of last month with hourly precision, and for the rest of ranges with daily precision. Acceptable performance of such 100 queries is under 5 seconds. So how we can solve such a problem? First approach, naive. We have database with index, organization ID, timestamp. We collect data in sets grouped by organization ID, hour. Query database by organization and range. We retrieve sets. We merge sets. And finally return size of the final set. Well, this approach has a lot of problem. Efficient query needs at least 11 gigabytes of RAM. It's extremely slow. It needs at least 44 seconds for one query. Under optimistic assumption of retrieving 2 billion of users because of duplicates, adding to hash set take about 20 seconds on 3.5 gigahertz core. Moreover, we must retrieve these users from disk. It would take at least 32 seconds for average SSD drive. So, for example, if you have 6 times 3.5 gigahertz processor with 176 gigabytes of RAM, it would take at least 5 minutes for such 100 queries. It is unacceptable. So maybe some distributed approach. Yeah, MapReduce. So we have 1,000 of working nodes. We compute hash for each user ID, here. We spread users with hashes across nodes such that sets of hashes in nodes are disjunctive. Here we count distinct users in each node, and finally some result. We can just add the results because we ensure that sets of users in these nodes are disjunctive. Yeah, great. So we have 1,000 nodes, 0.11 gigabytes of RAM per node, and total time of 100 queries is 4.5 seconds. Not bad. There is one problem. We just utilize 1,000 of worker nodes to solve our count district problem. How about solving the problem using my phone? Well, because perhaps your request for 1,000 nodes look like this, but it's usually look like this. So, count distinct using phone resources. What do we need? 2 gigahertz core, 450 megabytes of RAM, 10 gigabytes of disk space, and total time of 100 queries is 0.6 seconds. Wait, what? 10 gigabytes of disk space and 90 petabytes of raw events? Is it possible? Not exactly, but it is possible to serve accurate answers with high probability. How? Using sketches. Sketches is a bunch of data structures, algorithms, which are one pass, that means that algorithms need to touch only one item. If you have a stream, it needs only to touch one item to compute final result. Small in size, fast to update, fast to merge without losing accuracy, and able to serve approximate result, usually a trade-off between space, accuracy, and probability. What does it mean, trade-off between space, accuracy, and probability? Well, the most general answer is the more space, the better accuracy, and the higher probability, the worse accuracy. So back to solving count distinct with phone resources. How we can solve the problem? We keep sketch for each organization and time windows. Time windows are hourly, daily, and every 100 days. And assuming events could be processed when they are created, when event comes, I feed corresponding sketches with it. And finally, when the query comes, I retrieve corresponding sketches and merge them. So, great. And what you're gonna do if an amount of users grows 100 times? In first approach, you have to wait and wait, and wait, and wait, or build some 100 more powerful hardware. In distributed approach, also using sets, not a problem. You only need 100 more nodes. And using sketches, yeah, absolutely nothing, because sketches are orders of magnitude smaller than data they are represent. Of course, we are not going to compute everything using for. For example, if you want to process whole data in acceptable time, we need something more powerful. With sketches, we can easily scale our computations to the distributed system, because you can scale your system horizontally using arbitrary partition, and you can predict resource usages for each worker node, because sketchers are small and fast. And streams love sketches. Sketches are one-pass algorithm, which is usually a requirement for efficient stream processing system. Sketches are small. Size is usually with upper bound between 1 kilobytes and 100 kilobytes, and that means that you can pass sketch forward the stream, and sketches are unlikely to be a bottleneck in the stream because they are fast. So now I want to present some examples of problems which can be solved using sketches. For distinct counting, we have HLL, CPC, and Theta. For quantiles and histograms, KLL and T-digest. And for frequent items, Misra-Grace algorithm. Distinct counting. We have 3 sketches: hyperlog, compressed probabilistic counting, and Theta. And now I want to briefly summarize these 3 sketches. Well, which one to choose? It depends what you need. If you only need the union of set sketches, then hyperlog or compressed probabilistic counting would be a better choice. But if you need intersection or differences of set sketches, then Theta would be a better choice. I've mentioned that if we need only unions of sets, the best choice would be HLL or CPC. So first, a little comparison of these 2 sketches. Now, I represent a history of evolution of this algorithm. In 1985, Flajolet and Martin invited algorithm for distinct counting. In 2003, Durand Flajolet invited log-log, which beats FM algorithm. In 2007 was invited hyperlog-log, which beats log-log. In 2013, even better hyperlog-log, and 2017 back to FM algorithm. So Lang invited better estimator for this FM algorithm, and in fact, this structure with his estimator beats the best hyperlog-log. So trade-off between accuracy and RAM is similar. If we consider only just updates, speed of such updates is similar, both for HLL and CPC. Speed, but if we consider updates and compression with serialization, then CPC is better. And trade-off accuracy to storage, CPC is better. So CPC is overall better than hyperlog-log. However, its superiority isn't smashing. And for more details, I refer to excellent paper of Kevin J. Lang, Back to the Future, and even more nearly optimal cardinality estimation algorithm. Okay, so now, hyperlog CPC versus Theta, if you only need unions. Hyperlog and CPC serve similar accuracy to Theta using 16 times less memory, so no reason to use Theta. But if we have intersection and differences, we can using inclusion-exclusion rule with hyperlog and CPC estimate intersection and differences, but in fact it doesn't work well. And intersection and differences in Theta are no problem. For example, if you have 3 sets ABC with similar size, and size of their intersection is about 10% of each set, then Theta serves similar accuracy to HLL or CPC using 4.9 times less memory. But mathematical error bands for Theta intersection and differences aren't very straightforward, so for more details, I refer to DataSketch's webpage and Lee wrote sketch equations paper. Next, quantiles and histograms. Now I want to summarize two sketches for computing quantiles and histograms. So what are quantiles and histograms? We have a stream of values of size n, and k over n quantile is which value is kth value, while histogram answer question how many values was in value range from A to B. Yeah, these are very useless summary of your data. Useful. So a little comparison. Domain, T-digest works only for floating point numbers, while KL works for arbitrary domain with arbitrary order. And accuracy of quantiles, KL has mathematically proven error bounds, independent of both distribution and stream messages order. For uniform normal distribution, T-digest is better. For growing blocks, KL is better, and this is example of some nasty distribution and order of your data in which T-digest doesn't work well. And for quantiles very close to 0 and 1, T-digest is better. Okay, and speed. Updates. KL is about 3 times better, and while serialization of KL is a little bit slower, deserialization of KL is faster than T-digest, and if we sum up deserialization and serialization, KL is about 1.3 times better. Okay, so I want to show you some charts which present comparison of sketches estimates to exact values. It isn't comprehensive analysis of accuracy of sketches, rather evaluation of simple example to convince you that sketches don't bite. Yeah, distinct count, hourly, you see, blue line is exact values, red is theta, and yellow is hyperlog log. Yeah? Every 4 hours. Okay, this is set differences, so result from set differences, and comparison of blue line is exact values and red is estimate from theta. And the same for every 4 hours. Okay, histogram from KLL. Blue columns are result from KLL and red are real exact values. Not bad. Quantiles, yeah. Do you see blue dots? Yeah, they're behind the red one. Seriously. Okay, most frequent. Here we have the query was 30 the most frequent items. This chart shows how much of 30 the most frequent items returned by Mithra's algorithm matches the real 30 the most frequent items. Yeah, not bad result. And here is shows the 30 the most frequent items along with number of occurrences. Yeah, red is estimated result and blue is real hits. Yeah, so sketches rules.
Okay. So thank you, Miron, for the actually interesting part of this presentation. Now let's move on to what we've actually prepared for you to connect all those information that can be a little bit overwhelming, but extremely useful. So how can one of you use actually this information? Well, probably some of you use Kafka Streams now. So how can you join those two concepts actually? There are some advanced data analytics operators in Spark, like Bloom filter, count sketch, HLL, using like library like Spark Alchemy. But for Kafka Streams, well, not much. You have this aggregate operator that I've mentioned before, and that's it. You need to just integrate all of these structures by yourself. So actually, what we've done, we did that. So we are introducing a probabilistic data structures for Kafka Streams library, shortly Kafka Streams PDS. And what we've done, we've integrated a whole lot of probabilistic data structures, all aforementioned, like hyperlog, CPC, Theta, T-digest, and Mithra. And we made use of in-memory caches to for bigger structures, because whereas hyperlog log is about maximum 10 kilobytes, data sketches may be from 100 to, let's say, 300 kilobytes, and that's quite a lot. So if you aggregate the data in Kafka Streams, you need to remember that every message is serialized. So the serialization overhead is quite important. So we've made use of in-memory caches in Kafka Streams to actually spill the data periodically and contain the information about the structures in memory. So we support both windowed and non-windowed aggregations, as well as both stream and wall clock time semantics. The last part wasn't actually described by me here, but you can find this information in Kafka Streams documentation. There's not much time to describe it now. And as well, we've made a step to make serialization much easier using Kafka threads and our library GenCodec. So once again, remember the first example of unique word count. Oh, something's wrong here. Okay, never mind. The first example I was talking before, right? So you just need to provide the builder. Where's the button? The builder, and you need to group by the keys and window and perform aggregate, right? And this is not very performant. We don't want that. We want to use what? Hyperlog log for the big data. And this code actually comes from our library. What you need to do is to provide the builder, stream the data, and use our operator HLL, and provide something like a spill period. As I said before, you need to focus on the data structure size. So here we say every 5 minutes the data will be serialized to our state stores and follow to the changelog topics of Kafka. So as you can see, this is extremely handy. We come with 4 lines of code. If we like inline this piece of HLL, which I don't recommend. The windowed example, this is windowed HLL. We specify spill period, and we also specified time windows, as well as you can specify those time windows right here in the windowed by. Okay. And you started, and you can start using hyperlog log or other probabilistic data structures just like that. So yeah, when's the release? It will be soon. Actually, we've tried to introduce the library today. We didn't manage to, but it will be released soon. So you can find it on the AV System GitHub. And when it will be released, feel free to contribute. So yeah, thank you. We didn't have much time left to discuss more Kafka Streams related subject, but you can meet me at Krakow Apache Kafka meetup. I will try to do some more talks about Kafka Streams and the ideas behind this library using processor API and so on. So yeah, thank you.
We have, according to plan, we have 1 minute. So, and there are a couple of questions actually. So, will you be here for the rest of the day on the conference?
Yeah, sure.
So, feel free to ask guys the questions that you ask, because I see there are interesting questions. I'm going to pick one, the one that was the upvoted, the most upvoted, and the question is: are there cases where the differences between actual data and estimation are significant? Do you need a further maybe clarification to the question?
Yeah. I think in some sports it might be if you are counting when for example when you have 100 of the best results, and it really matter what will be in this 100 the best results, for example. But I'm just I just made up right now, so.
Yeah, this is not easy to find an example like that, but I bet there are some cases that you can't use probabilistic data structures because those are probabilistic results, right? Sometimes you need to focus on the exact result. It is pretty hard now to just find one of the examples, but I'm sure like in some minutes we will find the scenarios for you. So later you can find us here.
All right. So as I said, I'm not going to ask any more questions because we are out of time. But feel free to catch up with guys and ask them the questions. And for now, we have another presentation in 10 minutes by Renato Cavalcanti, and the presentation would start precisely at 11. Thank you.